From these crazy scorching heat waves to historic floods, it really feels like our weather has gone completely off the rails lately. But what if the answer isn't in our own backyard, but actually thousands of miles north, in the rapidly melting Arctic? Today, we're going to explore that startling connection between the very top of the world and the weather right outside your window. I mean, you've probably asked yourself this exact question, right? It feels like the weather just has a totally different personality these days. It's more intense, way more unpredictable. One day you're dealing with a heat wave, the next it's a flood. So what on earth is going on? Okay, so the main culprit we need to put under the microscope is the jet stream. Think of it like a fast-flowing river of air, way, way up in the atmosphere. Normally, it's what keeps our weather systems moving along. But sometimes it gets stuck. It gets locked into these huge, wavy patterns, just like the one that tragically steered Hurricane Sandy on its destructive path. When that jet stream gets stuck, extreme weather can get locked in place for days on end. This, right here, is our crime scene. All right, to solve this mystery, let's start with the evidence we're all seeing, the stuff that's happening right here on the ground. Just think back over the last few years. We've had these seemingly endless snowstorms one winter, and then they're followed by absolutely scorching heat waves the next summer. These aren't just random, disconnected events. Nope. They're part of a bigger pattern of increasing extremes. And there's a growing mountain of evidence that points to one prime suspect behind it all: the rapidly, and I mean rapidly, changing Arctic. But how? How can a place that's so distant and frozen cause so much chaos for the rest of us? Well, it all comes down to this really powerful phenomenon. It's called Arctic amplification. And in simple terms, it just means the Arctic is warming up much, much faster than the rest of us, at least twice as fast. See, as that bright white sea ice melts, it reveals the dark ocean underneath. That dark water then absorbs way more of the sun's heat, which in turn melts more ice. It's a classic feedback loop that just keeps accelerating the warming. And look, this isn't just a theory. We've got the data to prove it. This chart here is plotting temperature anomalies over the years. Just look at how those lines are diverging, especially after the year 2000. That top line, the Arctic, is shooting upwards way faster than the line for the mid-latitudes, where most of us live. That growing gap in temperature? Well, that's the engine driving all these changes. So here's the crucial part. The jet stream gets its power from the temperature difference between the frigid Arctic and the warmer south. Think about it like a river flowing down a steep hill. It's going to move fast and in a pretty straight line. But as the Arctic warms up, that hill, that temperature difference, gets a whole lot gentler. So what happens to our river? It gets weaker, it gets slower, and it starts to meander all over the place. And this brings us to the next piece of our puzzle. What does a weaker, slower jet stream actually look like in the real world? Well, a slow river doesn't flow in a perfectly straight line, does it? It meanders. And the same thing is happening with jet stream. Instead of just zipping straight from west to east, it's taking these huge looping detours, dipping way down south and then swinging way up north. To put it simply, it's getting a whole lot wavier. And this isn't just a feeling. Scientists are actually measuring this change. This table compares how often these super wavy patterns are happening now versus before this whole Arctic amplification thing really took off. And wow, just look at those numbers for autumn. A 65% increase over the Atlantic and around 40% over Europe and Asia. That's a massive, massive shift in how our atmosphere behaves. And this slide shows you the physics of how it works. It's a chain reaction. When you have low sea ice in one specific area, say the Barents Kara Sea north of Europe, the ocean releases a ton of extra heat into the air. This heat creates a big northward bulge, or a ridge, in the jet stream. That wave then forces a deep southward dip, a trough, downstream, which in this case is over Central Asia, and that trough delivers a blast of frigid Arctic air. It's a direct connection from the Arctic to our weather. Okay, so the idea makes sense. We can see the Arctic is warming and we can see the jet stream is getting wavier. But how do we actually prove that one is causing the other, especially when we're talking about just a single weather event? Well, this is where the science gets really, really cool. This is the million-dollar question, isn't it? We know the dice are loaded, so to speak. But can we say for sure that one specific roll of those dice, one single heat wave, one single flood, happened because of climate change? Answering that, well, that requires a really specialized field of climate forensics. So let me introduce you to the world of extreme event attribution. This is basically the science of fingerprinting. Researchers in this field are like detectives, trying to figure out how much, if at all, human-caused climate change altered the odds or maybe the intensity of a specific weather event that just happened. To do this, scientists basically have two main ways of looking at the problem. The first one is all about probability. It asks, did climate change load the dice to make this kind of event more likely? The second approach is about the event itself. It asks, okay, given that this storm happened, how did climate change pump it up with steroids and make it worse? Let's dig into these two approaches for a second, because they each give us a different but equally important piece of the final answer. So the first method is all about the odds. Scientists use these super powerful computers to simulate two different worlds. One is our world, with all our current climate change. The other is a fictional world, a what-if world without it. Then they just run the simulation thousands of times and count how often a crazy heat wave happens in each world. If it happens 5 times more often in our world, they can say climate change made that type of event 5 times more likely. Now, the second method takes a totally different tack. It says, okay, let's just accept that this weird weather pattern, this heat dome, for example, already happened. Then it asks a much more direct question. How much extra heat or rain did climate change inject into that specific event? So it's less about the odds of it happening and more about measuring the direct physical impact on the weather we all actually lived through. So let's look at a real-world case. Scientists were trying to understand European summer heat. They knew that a key ingredient for a killer heat wave is something called atmospheric blocking. It's basically a big, high-pressure system that just sits there and won't move. So they decided to analyze the temperatures, but conditional on how much of that blocking was actually around. And the results? They were just mind-blowing. The summer of 2014, it wasn't actually that hot overall. If you just looked at the temperature by itself, you'd say it was maybe twice as likely because of climate change. But, and here's the twist, 2014 had very weak atmospheric blocking. So once the scientists controlled for that, once they asked how unusual was this temperature given the fact that we didn't have the normal setup for a heat wave, the signal just screamed out at them. The probability ratio jumped all the way to 15, giving them what they call strong evidence of climate change's influence. So, which way is right? The probability way or the physics way? Well, the answer is both. The real cutting edge of the science now is focused on combining these two approaches. By looking at both the changing odds and the direct physical impact, scientists can build a much more complete and a much more confident picture of climate change's fingerprint on our weather. And that brings us right back to where we started. While it's still really tough to blame any single weather event entirely on the warming Arctic, the authors of that foundational paper we looked at, they conclude that these stuck, wavy patterns are exactly the kind of thing we should expect to see more and more of as the world keeps warming and the Arctic keeps losing its ice. The connection between a warming Arctic and our wild weather isn't some fringe theory anymore. It's a super dynamic area of science that's showing us just how interconnected our planet really is. The evidence is telling us that the very rulebook for our weather is being rewritten right now in real time. So the final question is, are we ready to play by these new rules?